Sequences. So we start with the definition of a sequence. And in the sequence, for a sequence, of real numbers is ordered and then list of real numbers. Here we start with A1, A2, A3, and so on. Let's keep on going and keep on going so it never ends. We not necessarily have to start at A1. Sometimes we'll start at A0 and then we'll write A1 and so on. Or in general, we might start at AK, then AK plus 1, and so on. As long as we know order of numbers and when we start and where we end. We're going to write the sequences. Notation. And the way we're going to write the sequence is going to be either we're going to list them explicitly. For example, we can write down A2, A3, A4, and so on. But for example, again, we don't have to start at A2, we can start something else. We can write the same sequence using the notation, something like that, and start to go to plus infinity. Or sometimes we'll just write down, or we'll just an and we'll say n, in our case, greater or equal than 2. Okay, so those are notation. Let me give you a couple of examples. It's a bit dry notation. So I'm going to write down the sequence, and I'm going to write down the sequence in 3 different ways. First one, say, I'm going to write down the formula for a sequence, 1 over n, and say n starts at 3 and ends at infinity. Okay. I also can rewrite the same one as, say, an equals to 1 over n, and n bigger or equal than 3. That's the second way. Or, and lastly, I can write down it explicitly, and I can write down explicitly as my first number is 1/3, because I started at n equals to 3. My next number is going to be when n equals to 4, 1 over 5, 1 over 6, and so on. That was the first example. In second example, I started with a sequence given explicitly. So explicitly. So I have 1/2, 1/4, 1 over 8, 1 over 16, and so on. Now I want to write down that over 2 ways. But you notice here we divided by power of 2. So if we're trying to guess, then the formula is going to look like 1 over 2 to n. And we start at n equals, the very first time we start dividing by 1 over 2 to 0, which is 1 over 1. So we start at n equals to 0, going toward infinity. Also, we can write down that as saying what is the formula for n is 1 over 2 to n, and n greater or equal to 0. That's the second one. Let's do a third one, just to make sure that you're comfortable. What is going on? Say we have sine of pi n. Start with the formula, and n starts at say 0 and goes to infinity. So what kind of formula is that? So let's try to figure out how we're going to get explicit. So we start with n equals to 0, then we go to n equals to 1, then n equals to 2, and n equals to 3, and so on. When n equals to 0, we're going to get sine of 0, 0. When n equals to 1, we're going to get sine of pi to 0. When n equals to 2, we're going to get sine of 2 pi 0 and 0 and so on. So you see what we actually have. We have is a bunch of zeros. So if you like, you can write it one more time, and that is like, you can clearly see what kind of sequence we're talking about. Often, when working with series, we're going to be interested in what is the limit of sequence. What it means which number sequence approaching when n is approaching infinity. So let me try to give you a kind of definition, but it's like intuitive definition. Okay, so let's kind of try to give a definition of what the limit of the sequence is. So limit of n equals to L when n is approaching infinity means when n is getting bigger and bigger, an is getting closer and closer to that L. Okay, that's kind of intuitive definition. That is intuitive definition. There is also a strict epsilon definition if you like, look it up. But for our purposes, that's good enough. Well, find the limit of the sequence 1 over n when n is from 1 to infinity. So we're looking for a limit as n approaching infinity, 1 over n. So what is going on here is eventually n is going to be huge. Eventually n is going to be infinity. So what we end up with doing 1 divided by a huge number, and bigger and bigger and bigger. If you take 1 and divide by a huge number, we're going to get 0. And that's how kind of we're going to use notation 1 over infinity instead of saying n is going bigger and bigger and bigger. Second example. Limit of cosine of pi n as n approaching infinity. So I try to guess what's going to be happening here. Eventually, I'm going to see in very big number for n. So eventually, I'm going to get cosine of infinity, and that is kind of, I struggle with what's going on here. What is cosine of infinity? So firstly, I want to get my intuition going. So what I will do is I will explicitly write down the sequence explicit sequence. If when n equals to 1, when n equals to 2, when n equals to 3, when n equals to 4, if I write them down, I may be able to see a pattern. When n equals to 1, I'm going to get cosine of pi. Cosine of pi is -1. N equals to 2, cosine of 2 pi is 1. Cosine of 3 pi is -1. Cosine of 4 pi is 1. So we kind of see our pattern, -1, 1, -1, 1, -1, 1. And you see, and if you look at this one, it's not going to be approaching any numbers because it's going to be jumping between -1 and 1. So it's not going to be close to 1 because we're going to have infinitely many -1s. It's not going to be -1 because we're going to have too many 1s. And it's not going to be, say 0 because we're always going to be not very close to 0, or we're going to be on distant 1/2 from 0. So we conclude that limit of cosine of pi n when n approaching infinity does not exist, period. Often we're going to need so-called squeeze theorem. So what does the squeeze theorem say? So if we have three sequences, an, bn, and cn, and bn is in the middle, so an less or equal than bn, bn less or equal than cn, and that is for all n. Now, if limit of an when n is approaching infinity equals to limit as n approaching infinity of cn and equals to L, then the conclusion is limit of Pn, which is in the middle, is also equals to L. That's when n is approaching infinity. So let's try to see why and how that works. So just imagine we have Bn, An, and Cn. And Bn is sitting between An and Cn. So what is going on is An and Cn is going to approach the same number. That's what this line is saying. That limit of smaller and limit of a bigger sequence is the same. Then with Bn, which is in the middle, will be staying in between these two numbers, An and Cn, on the left and the right. So it might go a little bit close to An, it might be close a little bit to Cn, but it has to be in between. So at n, it has nowhere to go but to the same destination point as both An and Cn. And it's important to see that An and Cn go to the same. If they'll go to different, then they're not going to have that squeeze theorem. And let me try and write down a quick example on squeeze theorem. Find the limit of cosine n divided by n, and from 1 to infinity. So what you notice here is cosine n over n is going to be between, cosine is between -1 and 1 in the denominator. What you notice is when n is approaching infinity, -1 over n becomes -1 over infinity, so it becomes 0. When n is approaching infinity, 1 over n becomes 1 over infinity, so it also becomes 0. So limit from the smaller, limit from the left and limit from the right, they're both approaching 0. So the term sequence in the middle has nowhere to go but to a 0 as well. So by the squeeze theorem, limit of cosine n divided by n, and n is approaching infinity, is going to be equal to 0.